It's only, yeah.
This is my homework. See, this is my homework page, homework one. And then I have another one for taking notes.
No, I use it.
Huh?
All right, guys. Any questions from homework so far before you get into?
And then I'm
So that one I was talking about in the
50
office,
pages into this.
is that one of those ones where I use law of sine or law of cosines to figure out the angle?
Not the one with the
The
formula
three
from the
triangles.
book. What was
No,
the other
three
one?
Look
triangles.
at it. Look at all this work.
The find tan of whatever that y is.
Yeah, you used the
The
tangent.
law of cosines to find the
No.
Why couldn't I?
Why would you?
Read these stupid things?
All right, guys. So has anybody tried out number 63 on section 7.2?
Yes. Can you repeat the question?
Let me write it down for you guys. Section 7.2, number 63. Let me put it up here. Booklets amongst y'all.
Better like to.
No, I said the three triangles. You knew what I meant.
This one.
It's the triangle.
Triforce. All right. So, the thing you got to remember is the section we're in is all about sum formulas and difference formulas for trig functions. I'm going to make you memorize the sine and the cosine one, but the one I won't make you memorize is the tangent one. In fact, tangent very often I don't make you memorize because you just build that off of other things. So there's a little tiny problem there. Let's make it a big problem. Yeah. There it is. Okay, I really like this problem because it's really, you got to be careful not to miscategorize this. I'm not trying to work angles into something necessarily, but that's where I start. But then it's really weird to figure out where to go from there at the end unless you remember what section you're in. They ask you two things, and the first thing is going to help you with the second thing. So how in the world do I start to show that alpha plus beta is gamma? I'm trying to show that alpha, that angle, plus that angle is somehow equal to that angle there.
You'll figure out angles A and B, and then obviously you'll find out the unknown angles of the two small triangles, and then with those you can find...
All right, let's try this out.
It's 90
What's
minus
true about these angles here? What are they called?
alternate interior.
No. There's no parallel angles here. Parallel sides.
Those are the exact same.
So again, what letter does it make?
A V.
Okay, so they are vertical angles.
There you go.
Beautiful. And of course, they have to be how related to each other?
Exact same.
They have to be equal to each other.
Yeah.
I love it. So it is kind of related to alternate here, but it's not that. But they do have to be equal to each other. How big is this?
90 minus alpha.
90 minus alpha. We'll look at it bright. And how big is this then?
90 minus
Sorry,
alpha.
how big is this then?
90 minus beta.
90 minus alpha, 90 minus beta, gamma, and of course they all have to equal.
180.
Alright, so the first part's done. You just set that up and do it.
Yeah.
Now when you look at the second part, you get worried. If you don't realize that they asked you the first part to help you with the second part. What is tangent gamma equal to immediately, based off of what we just did? Tangent gamma is the same
Alpha
as
plus tangent.
Sine over
tangent alpha plus beta. You can't distribute tangent, of course, because it's not multiplying, right? But I do have a sum formula for tangent that you can look up. I don't make you memorize it. This is just homework, so you are allowed to turn the page back. So I know that tangent gamma equals tangent alpha plus beta. Look up the formula for this. Because what's the tangent of alpha?
4 over 6.
Good, 4/6. And you know the tangent of beta?
4 over 3.
So if you could rewrite this in terms of tangent alpha, tangent beta, which is of course exactly what sum and difference formulas do. They try to tear those back apart. So that problem is nowhere near as bad as it looks like it could be. Right? Maybe. So that's as much as I'm going to say and do for that problem.
So you don't want to find the angle.
No, don't do that. You could. You totally could. Inverse tangent will give you alpha, right? Totally. but I'm not sure, and you'd have to do a lot more work to get to the point where you know enough to figure out.
The tangent.
Yeah, that would involve, like you said, some laws of cosines and sines possibly. You don't know how long this is. How long could it be?
As long as it wants to be.
Almost,
Really
not
long.
really. It's kind of set by this angle. See that? It's got to meet at a certain point, but then finding how long it is, that would be a neat problem. That would be.
Oh, this wasn't even looking at it.
Oh, I put it there for a second, and then I was going to do stuff up here. Where are we at, sorry?
You said how long is it?
Yes,
As long as
And you said it'd be an interesting problem.
it would be.
Yeah, that's it.
Okay, but then somebody else said something else, and if that's okay, okay, good. All right. Anything else from homework? Yes.
69 is, well, says use the
Which section?
division formula, but it has a coefficient, so I don't know how to do it.
Which section, sir?
Oh, 7.369.
Okay. All right, so this guy here,
No, 7.3.
7.3, right? So this here?
Oh, 'cause I thought you like had your head
69?
I was like, they need to go this and that. This is awkward.
So you sure it's 7.3?
What page are you on?
507.
Okay,
That's
so that's
7.2.
That's all right. We'll figure it out. No, this is, I hate when they do that. It's evil.
Yeah.
Because the 7.3 starts down there. Trust me, I've done that. Students love when they do it. So let's see, 69. It's got some weirdness happening.
Oh, yeah.
I like it. So now we're talking about sine waves and stuff. True. Two identical tuning forces are struck. One a fraction of a second after the other. Sounds produced are those. There's two sound waves interfere to produce a single sound. Blah blah blah. So if they're playing together, what actually happens is you get either destructive or constructive interference, where if the waves overlap, they get stronger. But if one wave overlaps with a trough, then they cancel each other out a bit, right?
And that's
So it's kind of a neat idea. Use the addition formula for sine. So all the addition formula for sine cares about is that this is sine of that angle plus that angle. So are you concerned about that letter
No,
there?
the C.
The C doesn't, it's just sitting outside, right?
Okay.
So it's C times this that I'm going to rewrite. So it's still going to be C times however it becomes next. So that C doesn't mess me up at all.
Okay.
Yeah. So this is nowhere near as bad as it seems either. You just have to apply that addition formula for part A. And then part B, they just want you to throw some actual numbers in to see what happens. But I love this kind of problem. I mean, this is exactly what we're talking about. Tuning forks, and you can model it. You turn on your oscilloscope, and you can see the sine wave going that measures that frequency of the sound. Cool? Yeah, I know. I'm doing that. Okay. Maybe. Thank you, camera person. Anything else from homework?
No.
All right. Does that mean homework is going okay?
Yep.
Or does it mean I don't want to look at it because I feel better if I don't think about it? Is that what it means? All
That
right.
means it's not the weekend yet.
You do feel better, but it's an unhealthy better. Sorry. Don't do that to yourself. Let's see now. So, what did we figure out last time?
We did the 2 times angle thing.
I like it. So, yeah, the last thing we
Started
did,
doubling.
we
Yeah.
used
And triple. We tried to do triple and we were
we
like,
used this idea. Use that idea to figure out what sine of twice some angle would be. And we plug it all in, you get sine, cosine of the same angle. So you get 2 sine, cosine. And trust me, for example, for things in calculus, it could be easier to do certain things with that, or it could be easier to do certain things with that. And they both represent the exact same idea. So you just use the part that's easier to do stuff with. I tried to explain what this was. And let's look at this a little more directly. will be sine of 2 theta plus 2 theta. I just really want you guys to realize the form of this is whatever's being doubled in here gets put there and there. This is always 2. Always. Because how many terms are there in the expression for this?
2.
2. That's why it's 2. Because I'm adding like terms. So this doesn't become 4. Right. So if I did exactly like we did the other day, how do I rewrite this?
Sine, 2 sine. Oh,
11 plus sine 2 theta goes sine 2 theta. Good. Keep the tone even.
And you get 2
Yep, you get 2 of these things. Of course, no matter what I put in there. So if I put sine of 10 theta. No, Jeff, make it 0. There it is. Two sine of
5 theta.
5 theta. Cosine of
wait.
5 theta. Alright, let me split it.
Yeah.
So of course this makes all the sense in the world when you have some kind of even multiplier here, right? And of course we talked real quickly, we didn't do it, but you could rewrite this because they're both double angle formulas and we know the double angle formula for each, right? How are we doing so far? Anything up there that's weird? Yeah.
What was the double angle?
We're talking about it right now.
Okay. Maybe.
And this happens so often in mathematics, you gotta think way back. What does sine mean? What does sine by itself mean?
X over
Y over R. It's the ratio of two sides of triangles. What have we done with it? And what do we continue? We continue to do all this weird shit with it. But never forget, sine can never mean any more than that. That's what it really means. That's it. But we can do a lot of stuff built off of that. So what I'm trying to say is you start to get lost a little bit with these expressions, but they're built off of things that we know are true. We know this is true. We proved this the other day. So I know that no matter what I put in there, I can rewrite it. And I just happened on this problem I could rewrite more of this. Let's go crazy here. Here we go. Here's sine of 2 theta, cosine 2 theta. So what's sine of 2 theta?
1 minus cosine.
Good. 2 sine theta, cosine theta. Is that cool? That's the double angle formula for sine. Who remembers this one? What's one way to write that? Cosine 2 theta?
cosine squared. Cosine theta.
I'm still lost.
Yeah.
Yeah, extremely lost.
Okay.
Minus
Hold on. We got here a minute ago. Is everybody with me here?
Yes.
Okay, good. We haven't done much past this, besides realize this says sine of 2 theta. What is sine of 2 theta? Replace it with what it is. What is sine of 2 theta?
2 sine theta.
Oh, okay.
Okay. That's all I'm doing. If I see a sine 2 theta sitting somewhere, what am I allowed to replace it with? This. Why am I allowed to replace it with this?
Because that's what it
It's
is.
the same damn thing. So whichever one, I don't know which one of these is more useful right now, but I'm just saying, you could rewrite this expression like this if you wanted to, if it was useful. If it wasn't useful, I wouldn't do it. But, so what's the cosine 2 theta?
Cosine theta minus sine.
Yeah, the basic one I try to get you guys to remember is this guy. And then you can build off of that. And it doesn't matter which one of the three you remember first. You can always build and capture. This is the one identity that actually has 3 options. So the other option would be
2 cosine squared theta.
good. And the other option is
1 minus 2 sine theta.
how are we doing? Is that cool? And of course that's just replacing cosine squared with 1 minus sine squared to get this. Or replacing sine squared with 1 minus cosine squared to get that. So you start, sine squared plus cosine squared equals 1. Why does that identity have to be true? Why? What's sine pick off from the unit circle triangle thing? What does sine pick off from that? Why? And what does cosine pick off? So, and we know a unit circle, x squared plus y squared is 1. So that is just the fundamental starting point. Sine squared plus cosine squared is 1. And we see this come into play. It immediately created 2 more identities, right? The minute I realized sine squared plus cosine squared is 1, I divided by sine squared and got 1 plus cotangent squared equals cosecant squared, and I got the other one with tangent and secant. I immediately got 2 more identities that aren't like obvious, but I built them off of something that was. So in mathematics, you have to be comfortable with, okay, I know this is true, I know this is true. If I put them together, I get something that looks weird, but I know it is also true, because it's built off of something I know is true. That's how we kind of develop other things in mathematics. Now, on that gray sheet that most of you guys got, if you haven't gotten it yet, email me or come to see me in the office. There's a whole lot of identities. The one on the top you have to memorize. The one on the bottom I don't make you memorize. How many sheets could I give you to capture all the possible identities? I would never stop printing them off. So at some point we go, let's have a basic set of identities and I can build the other ones as I need them. Right? We already see that. You don't even have to memorize all 3 of these. You can build the other 2 off the first one. But they're all based off of stuff we know is true. Okay, maybe. So what could I put here?
Cosine squared theta.
Yeah, I could put cosine squared theta minus sine squared theta. Now, just to kind of show you, where would it be useful to do this kind of thing? It wouldn't really be useful to do this. If I was setting it equal to 0, I could factor this, sine theta 0, cosine theta 0, so forth. You guys semi with me? I mean, I could break things apart a little bit easier. But to tell you honestly, it's just as easy to do it from this point. So the only reason I would do this to this is possibly some calculus kind of stuff. But realize you are allowed to do it whenever it makes sense. Okay, maybe. So the most important thing right now for you to realize is this step was not important at all. This step here was not important. It's just an example of what you could do using the identities that you're supposed to memorize. Yeah?
Is that kind of why, like, a few days ago you said that this type of math is much more guess and check? Is it because of those things?
Not so much guess and check, but let me try this.
Yeah.
That didn't take me somewhere. Let me try something else.
So it's those things that's what causes.
Yeah, it's all the different ways to write these things and all the different ways to apply them. Right? So as a student, you can feel one of 2 ways. You can go, holy shit, how the hell am I ever? And the other way to feel is, all right, cool, let me try this. All right, that didn't work, let me try this. That didn't work, let me keep trying something until it works. So right there, I'm going to see what kind of student you are based on how much stamina you have to get through some of these identity problems. So what I want to do right now is to build the next little selection of stuff. We have one set of formulas for lowering power. So what that means is, if I took this guy here, solve that for cosine squared. And real quick, before I forget, that trig handout is also on the website, but it's under my Calculus 2 class. So I put that trig handout up there for them, because unfortunately a lot of them had trouble remembering their trig stuff. So, but you can access it there too if you want to, print it out from there. So Corey, what do you get when you solve for cosine squared?
Got 1.
Yeah, 1 plus cosine 2 theta over 2. Not a big deal. Right. If I did the same thing for the last possibility, solve for sine squared, the only difference would be you'd have 1 minus cosine 2 theta, right? So if I solved, I would subtract that, add that, so you'd have 1 minus cosine 2 theta over 2. It's a nice symmetry between the two. So sine squared is 1 minus cosine 2 theta over 2. Is that okay? You guys could do that. You could solve for sine squared, right? So accept it. Or do it and make sure that I'm right. So they got these two. Now, why do you think they call this power reducing formulas? What power did you start with on this side? Second power. And what power is on the trig function over there?
2.
No, it's not a power. That's a coefficient on the inside. It's a first power, right?
Oops.
All right, so there's the power reduction.
Does this have the root thing, the radical sign on there? Is that
No, because I didn't take a square root yet.
Oh, okay.
I didn't need one.
Okay.
Yeah. Now, what's really funny to me, if I took, now this is another idea with this form, the form of these identities is what's important. And this is on page 510, so be very selective about notes you take. I mean, this is already in the book. If I were to, let's try this. If I had cosine squared of 3a, how could you rewrite that? Using what? How did you lower the power on that? What do you know cosine squared of what? Of any damn thing, you know. So what's cosine squared of 3a?
1 plus cosine of 6a.
Beautiful. 1 plus cosine of twice whatever the hell is in there, divided by 2. Do not make more of this than it is. It's exactly like when you first learned functions, and I said, okay, f of x is 3x over x minus 1. I said, okay, what's f of a plus h? You shouldn't have any trouble with that, and this is really exactly the same thing. If I know cosine squared theta, I know cosine squared whatever the hell you want to put in there. Yes?
Do they have the formulas you boxed in the book? Or
Yes. It's on page 510 at the top.
Okay.
Cool. Now here's where something else comes in, was based off something somebody just said. Because of this double angle here, so what I don't know yet, and from the title of this section, you know we're going to talk about half angle formulas. And the thing I want you to realize is if I have a double angle formula, that means I have a half angle formula, period.
No, you erased the thing over there.
I did. It's gone.
So the only thing that changed in is just the 6 alpha instead of theta.
Yeah, so it doubles whatever was there. Yeah. So, for example, here's another one. If I had cosine squared of x over 2, what would that be?
1 plus cosine x.
Yeah, 1 plus cosine of x, because I double the half, and of course I get back over 2. And if I take a square root, I get cosine of x over 2 equals... Is that the one you're thinking of? It's crazy. So why do you think we call it half angle? Because we are really creative people, because there's half of an angle in there. And what do you call this? It's called a Fred. No, it's called a half angle. So again, we did one the other day, a different way, but we can do it now a little more directly. We did like, I could do the same thing with sine. Let's capture that real quick. Of course, sine would just look like what?
1 minus.
Yeah, 1 minus cosine x over 2. Now, why do you think that plus or minus is there? Do you think the answer is just always going to have plus or minus?
Because it's
Depends on which quadrant you're in. 11. So if I said, what is sine of 15 degrees?
Can you slow down a little bit for me, please?
Okay. So again, these are in the book. Don't waste time writing them down.
They're also on your trig identity. So
They're on the trig identity sheet. Yeah, I tried.
you need to find the 30 because you want to.
Yeah, so then you just ask yourself, this is what it's for, right? This is why it's called the half angle formula. That's exactly half of an angle that I know. So the other way to write that is sine of
30
30
over 2.
over 2 And now I just plug it in. Yeah. So it'll be plus or minus. And is it going to be plus or minus?
Plus.
Because it's in the first quadrant, right? So it'll be square root of 1 minus cosine of 30, because that's what's there.
Yeah.
All over 2. What is the cosine of 30? Good, I like it. 1 minus rad 3 over 2 over 2. If you give me that answer, it's not really good enough. You got fractions inside of fractions. That's no good. So how do you clear that? How do you clear that internal fraction?
Minus.
So what I got so far, I got sine 15. So how do you kill that internal fraction? What do you want to do to kill the over 2? You'd like to multiply by 2, and thank God you have another side, like you would in an equation that helps you do it, so you can multiply top and bottom by 2. Don't let little things like that be a problem. Right? You know how to handle fractions inside of fractions. Just clear the denominator. And to make it legal, you have to do the same thing to the top and bottom. Right? So what do you get?
2 minus root 3 over 4.
I like it. But you can even go further with.
1/2.
Good, I like it. So root 2 minus root 3 all over 2, because that's what the square root of 4 is. Good. So there's another way to represent the exact answer for sine of 15. We did sine of 15 the other day by realizing it was 45 minus 30, right?
Mm-hmm.
And then we could just use the difference formula. Okay.
Sorry.
That's all right. Get it out of your system. That's all right. Okay. So there's your half angle formulas at the bottom. Again, you need to memorize the ones for sine and cosine. You don't have to worry about the ones for tangent.
Can you repeat that?
So on your sheet,
Yeah.
yeah, it's up here. So the sine and cosine, anything above that black line on the trick sheet I gave you, you must know. Anything below it, if I ask you a question involving it, I'll give it to you on the test. All right, don't make you memorize the ones below.
Not to use it still.
Yeah, you just have to know how to use it. And most of them are just plug and shut. Yeah. So there are several homework problems that I refer to something I didn't even talk about. There's one very specifically that refers to something at the bottom, page 504. Sums of sines and cosines. It's this whole little formula. It's because it's not the most used formula in the world, but I want you to realize things like that exist. So I assigned you homework. So all that is a plug and chug situation. Figure out what A and B are and put them in the right place.
What is that funky symbol?
I don't know what you're looking at, so.
Circle with like a...
Oh, okay. So you got, what's this one again?
Yeah.
Theta. This dude, yeah, but it's phi. D phi Fulham exact. Good. It's just another symbol they use for angles. Right, so you will see lots of Greek letters just flying around here. We saw alpha, beta, theta, gamma,
So gamma is the
Here's
one that kind of looks like a Y?
phi, or phi. Huh?
So gamma is the one that kind of looks like a Y?
Yeah, gamma is the one that looks like a fish standing on his nose. Or
kind of like
how do you make a fish? Don't you make a fish like that? Especially if you can draw as well as me.
That looks like a Y.
Depends on the font used.
It's a Y.
What's the one that looks like an F?
Beautiful. It's a curvy Y. Well, whatever gets you through.
Crows looks like an F.
Let's see.
Curves it F.
Yeah. What is Moll's formula of Malthade's?
Oh, yeah.
What is that?
Where was he at?
At the bottom of the handout you gave us.
Oh, yeah, I like it. Let's see. Oh, so if you have for any given triangle, now who do you think alpha goes with? Alpha goes with A, beta goes with B. It's like our big A, big B angles. So for any triangle, that's true. And you use it where it's useful. And how much have I talked about that formula?
Never.
Just now. So it is useful in very, very weird situations. And it might be useful even more places, but there are more useful things. So there are... you guys are not used to just taking something in math and playing with it. For one thing you didn't know you could, for another thing you really don't think you want to. Right? Somebody else can do all that shit. So there's a lot of little side notes in history that sometimes we'll rediscover and go, damn, that would be more useful now. And we just forgotten about it because it wasn't very useful back when it was discovered. And it's just somebody playing with identities and coming up with something. So this guy played around with ratios of things and figured out how it related to trig functions. And of course they should be related somehow, because trig functions are ratios of sides of triangles. But his little formula is not that useful, poor little dude. Right? But he's more famous than me, so what the hell? I can't say much. The last couple things in section 7.3, I'm not really going to focus on too much. The product of sum formulas, and that's just really playing around with sum formulas from earlier. And then sum to product is just kind of reversing, making it go the other way. There's a couple homework problems that involve those. You just look them up. You don't freak out. I'm not going to make you use them. They're on your sheet under the black line, so it's nothing you have to memorize. The reason I assign homework for it is just so you know they exist. Okay, so what I want to focus on today. Any questions on this here? You guys want to see any? Let's do a couple concrete examples of some of this, and then we'll do some new stuff.
Just a side note, I was in the math lab, and when I asked him the homework questions, they say, "Oh, you're in Waller's class, aren't you?" He always gives the hard ones. Thought you might like it.
Yes. Spread the word. I'll have a nice small pre-calc class next semester.
I know that's your Calc 2 is doing that for you, I think. I know quite a few of them too.
Oh, Calc 2. Oh, yeah, they're loving me. Oh, yeah, because they came in not knowing shit, so they love me. All right. Sorry. I gotta release some frustration. Not all of them, but I love it when the most vocal students about you do this and you do that are the ones that don't show up to class or don't do their homework. Ooh, I love that shit so much. Sorry. Gotta let it out.
Do you call them
Oh,
out?
blow up. Oh, yeah.
Right.
Sometimes. Oh, sometimes. Especially when it's just so blatant. I'm like, excuse me. You missed that day. Shut the hell up. So let's do a couple of concrete examples.
I would just be like, I would respect your opinion if you showed up to class.
What's that?
I would be like, I would respect your opinion if you showed up to class.
Pretty much. That's exactly what I'm trying to capture. So look at this problem. Here's one that looks like a problem we've done before. Oh, and this is even nicer than.
Oh my god.
Did you say nicely?
Well, it's nicer than I thought it could be. Well, because this is a nice right triangle, it's not going to involve any radicals.
Yeah.
But beyond that, what's the problem with this? The most common mistake is somebody thinks that they could just work this directly without using any identities, which is really bad. If I draw this triangle right now without thinking about it, put the 7 and the 25 in the right places, right? It's cosine, blah, 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 and just start to attack this. And then just twice something somewhere arbitrarily, that's crap, right? What angle is right here? What is this angle? Let me see.
The cosine, the inverse.
This is that angle.
Yeah.
What's supposed to be there? Twice that angle. How the hell are you going to figure that out?
I make it twice as big.
No, I don't want to go that way. You could go that way. It's not impossible. But it's close enough to impossible that I don't want to go that way. So, of course, what would I rather use?
Identities.
Yeah, we know that sine of twice any angle, specifically for us that angle, is
Sine 2, sine.
sine theta cosine theta. So here, what would this equal?
2 cosine inverse, or 2
Sine of,
Cosine.
right? Twice sine of the angle.
Cosine
So,
inverse.
The angle is this guy. Cosine of the angle.
you could put the cosine first.
So the big thing to realize there is this is just theta. This is an angle. So this is twice an angle, so I can use that double angle formula. Now my little triangle that I've drawn, I don't have to double a poor little angle dude. Because now it directly applies here, doesn't it?
Yeah.
In fact, that one
Awesome.
kicks so much ass. Exactly. Right? All that part becomes is 7 over 25. Kicks ass. And of course, if you look at triangle, it's 7 over 25. So either way you do it, you'll get there, right? So 7 over 25. What sine of that angle? So what do I need?
The other side.
Yeah, the other side. And the other side comes out to be
24.
24. I love it. So some of you guys are starting to realize you got 3, 4, 5, 5, 4, 13, 7, 24, 25. Cool.
So it's the inverse of that though.
Or you just do 25 squared minus 7 squared. Take the square root. You'll get to 24. So what's the cosine of that?
25 over 24? No, I don't know. 24.
Cosine will be...
But it's inverse cosine?
Sine, I'm sorry.
Yeah,
Oh.
Sine of that would be... 24 over 25.
25.
And then you got your 2 sitting outside. Yeah.
So the cosine inverse doesn't make a difference, technically?
No. Cosine inverse is the whole reason I could draw that triangle. It makes the biggest difference. Because cosine inverse represents physically what?
Oh,
An angle.
That's right.
Inputs for cosine are angles, so outputs for inverse cosines are angles. So this is that angle there.
We'd be screwed though if it was just cosine. It'd be
Pretty
way-
much. Well, it wouldn't be totally screwed.
Well, it'd be just way different.
You just throw it in your calculator because it's all you can do.
Okay.
Right? Now, obviously, you could throw this in your calculator and get an answer, but I ain't gonna like it. It's gonna be all decimally, right? And that's not what I want to see. If I see decimals here, then I'm gonna take most of your points, in fact, probably all the points off. You can certainly check this work, right? And you're like, yeah, those Cap 2 students are right. This guy's neat. But what do I get there if I just keep it as a fraction, multiply it through? 48 times 7.
A big number.
Big number, yeah.
336.
36.
They used calculators.
Yeah. They can use calculators, it's all right.
Bottom 6.
Yeah, 625. Good. That's the only answer I would accept. Because it's not reducible, for sure. Give me some decimal, no good. Now, if you give me that one and then a decimal, I'm okay. As long as you give me that thing.
It's not reducible?
Hell no. If the pieces weren't reducible, the result is not reducible, right? Okay.
Oh, I got the fraction. Just
I know, but I need to see the word.
I know.
I know you get a decimal and change it to a fraction. I know that button
Really
exists.
confused, but yeah, go for it. No, I'm kind of tired.
I understand that feeling. Okay. Not too bad, right? I mean, yeah. We've seen this kind of problem in every section where we do an identity, and then the problems they'll always have problems like this where they involve these inverse trig functions that you have to rewrite using the identity we just learned. Yeah.
Put your hand up so I can guide you up a little bit. Next one up. All right, the 2 sine, cosine, right? Okay. Now I know sine is the 24 over 25, but then where does the inverse cosine?
No. It doesn't go anywhere. Watch. All right, just look at this. Look at just this. Just look at that. What's the sine of theta?
24 over 25.
Where did the theta go?
It's still there.
Where'd the theta go? There's your answer. Where'd the theta go? That's what sine of theta is. So what's the sine of this angle? That.
Okay.
It didn't go anywhere. It was part of the problem, right?
Can we just like replace that with like say an angle? Like just put angle? Because I get confused when I see that.
Yeah, to be honest, if you call this theta right there, you could write 2 sine theta, cosine theta, and just reference your triangle.
Okay.
As long as you establish that you're going to call that theta, that's beautiful to me.
Okay.
Because then it doesn't look nearly as
Yeah.
loaded with stuff.
Less writing.
Kicks ass. It's officially called U substitution. Sometimes when you factor, your teacher, depending on who they are, might show you U substitution. So if you've never seen it, it's too bad for you. No. I mean, if I had shown you an example real quick, if I had this, if I had to factor that, This isn't really too bad, but if you want to make it look better, you can say u is 3x minus 5, and v is 7y plus 4, and now I got u squared minus v squared. That's easy. All right, so u substitution is exactly, and this, so you call this one theta substitute, but it's exactly for that reason. Take out the part that looks gross, it's going to be repeated, just so you can kind of focus on what really the question is asking. It's beautiful. I love it. Let me see what other kind of weirds. They're going to have a whole section where they say prove the identity again. And now it's going to be based off of the identities we just learned. Right? Blah, 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 blah. Oh, here. Well, no, I want the other kind. Where's the other kind? Where's the other kind? Oh, yeah, here we go. So what's sine of x over 2 equals what if sine of x equals half, 3/5? So obviously, what are you going to use?
The half angle.
Yeah. I'm asking about a half angle that you know. You know the full angle is 3/5, and you want to know what the half angle is. So use the half angle formula. We just learned it, but you need to know it by test time. Here, real quick. While you guys are doing that, again, before I forget, I finally get the second part of the homework and the timeline done. Our next test is going to be pushed back to November 3rd. So absorb that information, feel about it how you will, and it will happen then. Oh, what section are we on right now? Okay. 7-3.
Oh my gosh, we only have 1, 2, 3, 4, 5 seconds left.
You said November 3rd.
That's on here too.
I don't even realize that. Oh, yes. Dude, sick.
What's up?
Our final exam is the first week of exams.
I know, it's exactly the day after we review for it. It just almost never happens.
I'm really excited.
It's crazy.
Because I only have one final.
So if you didn't pick up on this, I'm just about 100% sure that I'm going to give us that Wednesday off before Thanksgiving. If that's okay.
Yeah.
Is that okay?
Yeah.
That's okay.
All right. If you have a problem with it, you can come here and sit here and do whatever you want to. I'm not going to be here. I'll probably get flack from my dean. This is brutal. Hey, Dean. How you doing? Like he watches my videos. I'm gonna get a phone call now in 2 days. From the other people I talked about earlier too. Great. Hey, Calc students, how you doing? Stop watching us. Yeah.
Is that test live on Monday or Tuesday?
I don't know. The 25th, that's a Tuesday. Because then the next day would be the last day before Thanksgiving, but I'm going to give us that 26th off. It also gives me time to actually grade the test, which is nice. So that way I grade it in one night. Alright, so how are we doing on this? In general, what does that equal?
1 minus cosine beta.
Plus or minus square root of 1 minus.
It's kind of easy to remember these, right? If it's cosine, it's plus because it matches. If it's sine, it's negative because it's the opposite of.
Yeah. So you make a triangle off the sine x. Okay.
You don't need to.
So, okay.
In this case, you don't need to. It's too easy.
Well,
And then,
But in general, yes. In general, since it wants cosine here, you will have to make a little triangle.
for that one,
But for
obviously.
this one, you should know
3, 4,
what the last side is.
3,
Yeah.
4, 5.
You-
So you would replace.
So this would be 3, 4, 5. So cosine of x. And which quadrant am I in? Did it tell me?
1,
It didn't. I didn't tell you, but it tells me we're in quadrant 1 yet. Where else could I be?
4,
No.
3,
No.
2.
Hey, how did you get that? Why could I only otherwise be in quadrant 2? Because sine is positive in 1 and 2.
Yep.
So they, in this little section of homework I'm taking this out of, they do tell you what quadrant is in. Otherwise,
It's
be a little mean. Because now think about this. This gets a little weird for us. Half of the angle, let me just give you an example. If I was in quadrant 2, what could my angle be? Anywhere from 90 degrees to
180.
So where could half of the angle be?
135. Oh,
Beautiful. So I'd be completely in the
second, third, first,
where's 45 to 90? First quadrant. Okay, you with me? So you do have to pay attention to what your angle currently is and where half an angle would take you. Does that make sense? Because this plus or minus is completely based on where x over 2 is. What's really nice is I know I'm in quadrant 1. If I were in quadrant 2, half the angle would take me back to quadrant 1. Is that cool by itself?
Yeah.
Because the biggest it could be is 180. Half of that is 90. That's effectively quadrant 1 as far as I'm concerned. It's one of the ones we have to know. But I'm in quadrant 1, so I'm from 0 to 90. So, of course, half the angle would take me
positive,
0 to
90.
which is still quadrant 1. So I know my answer is going to be
Positive.
positive. So it's positive square root of 1 minus.
4
Good. Cosine is
4
4 fifths.
over 2.
Let me stop right there.
So why are we not actually putting the 3/5 into any of this?
This is sine of x, and the identity requires me to know cosine x.
So that,
I can't put this here because this is a different angle entirely, right? So I can't use this here, but I can use this whole thing to figure out what cosine x is. Sine of x over 2 in general is equal to this. Cool? Sine of x over 2, we just
Why are we
proved it
using
earlier.
two completely different?
one for the triangle and one for the actual equation.
Two completely different.
Like, well, it looks like we're using two completely
So
different
watch this.
triangles to solve one problem.
So they asked me what this is, right? The problem asked me what this is. So I write the equation for it. One reason why I do that is because I got to figure out what I need to know. I need to know what cosine x is for this equation to work, right? They asked me what this is. The equation for it is this. How can I figure this out? I need that. What did they tell me? The dorks told me sine x, right? So how do I, sure, these evil people didn't tell me cosine x, those damn people. So how do I figure out cosine x?
You draw
Well,
the triangle.
I know the ratio from sine. I can then make a triangle to figure out cosine is, right? So that's why we did what we did here. It's asking me for this. How do I get this in general? This way. What do I need to finish this out is cosine. They didn't tell me cosine, but I can get cosine based off of what they told me.
So we should probably draw the triangles if it's given like that.
Definitely. Especially if it's a more complicated one, that they said sine of x.
Yeah.
Yes.
Okay.
Yeah, this one, the 3/5, you should just love that, right? Yes.
With all of these, should we assume that they're all going to be right angles? Because if you
Anytime, what did I say before, to be very careful? Anytime I have this expression, I can draw a triangle that represents, a right triangle that represents the situation. Now, did this necessarily come from this?
No.
No, and there might not even be a triangle that could possibly exist to fit what this is trying to say, but I can use it still to get the other trig functions. This is that representative triangle that exists only in my world, and it helps me get the right answers for any other trig function I want based off of him. So I try to say stuff like that. Every time we use this triangle, it could have been something that couldn't even physically exist, but I just need it as a representation to help me get something else. Yes?
So only works for right triangles, right? These identities?
Yeah, this to this to this only works for right triangles. Yes, yes. Cool. And how do I know I can use right triangles? Because sine of x is built off of.
Right triangles.
Yes, yes, yes.
Yes.
So, finishing this out real quick.
times by 2 over 2.
Yeah, multiply by 5, so 5 minus 4 is 1
Oh,
over 10. Is that right?
It's,
Multiply top and bottom by 5, you get 5 minus 4 is 1 over 5 times 2 is 10. And you know, whatever the hell that is. You can rationalize it. Root 10 over 10.
would you want us to?
Let me say it differently. You should rationalize it. Root 10 over 10. Okay. Yes, sir.
Can you do one more that's not a perfect square?
Not a perfect.
Square. Or like a
Oh, I
perfect-
see what you mean.
triple
Sure,
flat.
sure, sure.
Do cosine 1, 2. Yeah.
Do what now?
Don't do tangent. Well,
No.
you could do tangent.
Why not tangent?
Do tangent.
Yeah, we could do tangent, but let's not. Let's focus on what we got to memorize. If they give you tangent in the book, you just look it up. It's not a big deal. Let's see. So cosine x over 2 equals what? If cosine of x is negative 2/7 in quadrant 3.
please.
No, it's not so bad.
Is it clear to 5?
Why aren't you doing anything with the bottom too?
Because I have to. I can't multiply the top of the fraction and not the bottom at the same time.
No, why don't you multiply both by 2 for the bottom?
2 times 5 is 10. So I multiply top and bottom by 5 to clear out the over 5 that's in there.
Yeah, but you still got the bottom, the actual denominator of 2.
I don't care.
That's
The,
okay.
the reason I know to do something further with this is there's a fraction inside of a fraction. There's not a damn thing I can do about the fact that the whole thing is a fraction. But I can kill that internal fraction, right? Internal medicine for algebra. Complex fractions. Yes, sir.
Oh, wait.
Okay. Square root of 1 is 1.
You cross. No,
Oh,
cross.
multiply by 5. 5
Oh,
minus
both of them.
4.
Okay.
Yeah.
You both. Okay. I got it.
So in general, what's cosine of x over 2?
1 plus
Good.
cosine x
Because it matches
over
with what is 1, so it's plus. I'm in quadrant 3, so let's figure this out right now before we do any
X.
real
2.
work.
Negative
Half the angle would be where?
90,
Yeah. 90 to,
135.
which is in quadrant 2, and cosine is still
Negative.
negative. But you do want to do that very quickly for yourself to make sure. If it was a sine question, it would have gone from negative to positive, because half the angle would take me back to quadrant 2. How we go?
Good.
Does that make sense by itself? Shit. So if I would have asked for sine of x over 2, x is in quadrant 3. Where's x over 2? Well, what's quadrant 3? It goes from 180 to 270, right? That's quadrant 3. So if I cut the angles in half, where would I end up? Quadrant 2. So if my question would have been about sine, you can't just look there and go, oh, it's going to be negative. No, because half the angle would actually be in the second quadrant, and then sine would have been positive. Cosine is like it doesn't matter, really. Cosine's negative in both the possibilities, so it's going to be negative choice here, right? So you have to make this choice based on where this would end up. Yes, sir?
I didn't get that.
Sure. So it tells me that this x is in quadrant 3. So what could x be?
From
Anywhere from 180 to 270.
So how did you say you could take half?
Because it's asking me to. Yeah, that's all. It's not me, it's the
So
problem.
then that's why it goes from 90.
To 135. It's half of where it was.
Okay.
Cosine doesn't change, it's negative either way, but if I would have asked sine, it would have changed from negative to positive for the half of it.
I got it.
Okay.
Makes much more sense.
So I know this is going to be negative. Do I have cosine? Yes. Oh, that was too easy.
Negative
14 times 5.
Okay.
If I didn't have cosine, if I would have told you tangent here or something,
I did it.
what would you have had to do?
Draw a triangle.
Draw a triangle. You don't really even care about the negative. Right? Now, not at first. Let's do another one. I made this one a little too easy.
Just a little bit.
Negative 70 over 14.
I didn't get that.
See again, sir? What's up? What happened?
I didn't get what he said.
What did I say?
No, what he said. That's not the answer I got.
What did you-
Oh, I don't. Oh, okay. All right. That's okay. Multiply by 7. Right, to fill the 7.
Yeah.
7 minus 2 is 5. 7 times 2. 14.
Rationalize.
So you get negative square
That's
root
what I
of
got wrong.
5 over square root of 14 multiplied by root 14 to rationalize.
So 70.
Yep. Negative root 70 over 14. And I know 70 won't reduce because I know what went into it. 5, 2, and 7. So there's not 2 of anything. Okay, maybe.
Yep.
Let's not do another problem. I desperately need to get to the next section.
No.
There is no question mark at the end of that section. Yep. So let me ask you your immediate impression of if I ask you this question here.
Die, please.
Diocles?
Die, please.
Oh, Diocles.
There's my impression.
Directed towards the problem or towards me? This could be a problem. It needs to get a body right. That didn't help.
Oh dear.
So some of you guys, I mean, the answer is obvious, but at the same time, the real answer is not so obvious. I didn't tell you any restrictions on anything. How many answers are there?
3.
Infinitely many. Why are there infinitely many? Because what does sine look like? Forever. So how often does it equal negative 1/2? It's there, it's there, it's there, it's there. It's there forever in both directions.
Yep.
So it's like an infinite infinities. All right. So we just, thank God we don't have to make an infinitely long list. I just want to show you how to capture all the answers. You start with the easy answer. And there are 2 easy answers here, right? Where do the 2 easy answers exist? Where is sine negative? Yeah, the 3rd and the 4th quadrant, right?
Mm-hmm.
Now what angle are we talking about to make it 1/2?
30.
We stop right there. Yeah, so either way you want it, if I don't say, but let's try to stick with radians more often than not.
Pi over 7.
All right, so the reference angle would be pi over 6, and then you can build up. The actual angle would be, this is reference angle. Actual angle, yeah, 7 pi over 6.
11 pi over 6.
Beautiful, because it's 1/6 of a pi away from 2 pi's, right? Somebody ate so many pies, so that 11 pi over 6.
You only ate one of them. Yeah.
Still, I wanted all 2 of them from me. So if you say theta, let me stop right there. Is that cool by itself? I mean, that's sort of the reverse of what we're doing. So as long as you know all your values, you should be able to go backwards. When is sine 1/2 at 30-degree reference angle? Whereas in negative, those quadrants. Okay, now work out what the real angle is. You're kind of doing in reverse what we did before. And it's not that bad once you've done what we did before.
Mm-hmm.
So that wasn't really evil. Of course, I'm kind of leading you on here a little bit. but let me know if
So
it
it's
is.
gonna get evil?
Well,
Always gets evil.
a little bit. So there's two what we call base answers. There's two primary answers. Now, where would another answer be?
First and second quadrant.
Yeah, good, right? Exactly, good. I don't even want necessarily an exact answer, but another answer built off of this would be a revolution around. Because that you'd end up at the same place, wouldn't you?
Yeah.
And that, of course, is the visual representation of the idea that sine is forever, so you'll catch it infinitely many times, like I had up here a second ago. So all I have to do then is, on top of this, the one we just did would add how much? 2 pi. But I can do it again. I can do it again. I can do it in the other direction. As long as I'm adding, subtracting exactly 2 pi. So then the way we represent that is that
K.
where k is an integer. K is an integer. So if k were 1, that would represent 1 revolution around, right?
Okay.
If k were -2, that would be 2 revolutions backwards, right?
So you encompass the other part.
Yeah, so now in this one you do the same thing. So for sine and cosine, it's almost always going to be this. And why does it make sense? What's the period of sine and cosine?
2 pi.
Craziness,
Oh.
right? How's that by itself? Is that?
So it's the tangents plus pi.
Exactly. Good. Sometimes, now why couldn't I do like a smaller step? Because there's no way to go from here to there systematically. Because this is more than this. So I can't like set up one expression that captures both of those. I need 2 expressions to capture both. Because they're not equally spaced out.
Give me a weird look.
What if they were opposites? Like, what if they were...
I love it. Exactly. Let's try one like that.
Yeah, exactly.
So what if I had sine squared theta equals, let's just keep it the same. Well, let's keep it like this. 3/4. I like it. That's good. This will still work. So what do you have to do first? Square root. And anytime you pick a square root, you got to put plus or minus. All right, now you know the answer here. Fundamentally, you know the answer. Then you just got to work it out. How many quadrants will I look at for? Yeah, all 4. Because sine could be positive or negative. So, but what's the reference angle that ties them all together? Reference angle. Pi over 3. Yeah. Where's sine bigger when it gets closer to y? Right? So it's got to be 60 degrees, pi over 3. So I'm going to have pi over 3 here. Pi over 3 there. Pi over 3 there. And of course, pi over 3 there. Now I have 4 answers here, but do I need 4 expressions?
No.
No, because 2 of them are, like whoever just said a minute ago, what if they're exactly across from each other? This is exactly what I think you had in your mind, right?
So it's just a reference angle of pi.
So I need 2 base answers. So which do you think are going to be your base answers?
Pi over 3.
Yeah, this one, and that relates to this. So then this one, and that relates to this. So what are my primary answers going to be?
Pi over 3 and 2.
Yeah, pi over 3
2 pi over 3.
and 2 pi over 3. But now, the period of sine is still 2 pi, but it's just because in this problem they happen to line up across from another one, so I don't have to do plus 2 pi k now. I can catch the other dude that goes with him because he's exactly across from him. I don't have to go a full revolution around.
So it would be plus pi.
Yeah, so pi over 3, I just have to go half a revolution, either direction, and I'm going to catch the other dude on the way, am I? Not. Yes, there you go. Try to make it grammatically correct. Yes?
Is the distance between pi over 3 and 2 pi over 3 90 or?
Yeah, how far apart? 2 pi over 3 minus pi over 3. pi over 3. So I like the way you're thinking. You're thinking, can I catch all 4 of them in one go, right?
With 9, like,
But of course, how far apart are 2 pi over 3 and 4 pi over 3? But that's beautiful. What Dawson's trying to do is, okay, that's nice. You got to consolidate it to 2 statements, but it's still too much for me to write. That's how I'd feel. And then, so is there a way to capture all 4? And when do you think I can do that? It's not the only time exactly, but this is definitely the major time you can do this, is when your primary ones are on 45. Because then they would all be 90 of pi over. Then you could do a multiple of pi over 2. That's what you're thinking. But I'm not going to take points off if you have too many things here. Well, let me be careful how I say that. It's important for you to know when you can consolidate. But if you don't see something and you get the right answers, I'm not going to go overboard on taking stuff off. But in that situation, if I have 4 answers and they're all on 45 degrees, so if I would have said here sine squared theta equals 1/2, then it would have been sine theta equals 1 over rad 2, which is rad 2 over 2, which is 45 degrees. And I could have captured all the answers in one statement, right? Some weird math game show. So I get pi over 3 there, and I get 2 pi over 3 there. So my 2 primary ones, and then I add what to it?
Pi k.
Pi k, because now I only have to do half a revolution to capture a whole other set of answers.
It'd be just like tangent.
Just like tangent. So this isn't horribly evil, is it? It's actually built off of what we already know. I love it. The frequency of looks at the clock increases as time goes on. For some people, they're looking at the clock 2 minutes in. So what if you get one like this?
We do the plus or minus.
No.
It's thing.
0.65, is that radians, degrees? What is that?
Radians.
No, it's not. It's not an angle.
It's nothing.
Yeah, it's a ratio of sides of a triangle, so it's nothing. But it's cosine of what angle gives me this. So your answer, I'm trying to get you to do it in radians, sure, but you don't really think that you can convert that to degrees. It's not degrees. That's the angle here, right?
It could be feet, it could be inches.
So the only thing you can really do here, is that a value that you know?
Yeah, no.
No, so how do you solve this? You take
Negative.
inverse cosine. Yeah. So if I give you one that you don't know the value of, then you can use your calculator. If I give you one you do know the value of, you better not use your calculator. Because if you do use your calculator, then I'll engage your... Yeah.
Should we go into degrees?
Yeah, you definitely want to go radians. Degrees would not be wrong, but I'm just trying to get you guys steered towards radians.
0.86.
Especially here. 0.8,
632.
86,
32.
32, that's good enough.
So would you just want to write that then, if you wanted the exact answer? You're going to write that cosine?
Yeah, I'm never going to ask for an exact answer here because that's really not useful to anyone.
I'm just asking.
Yeah. Yeah, so I'm always going to want you there. And when in doubt, go at least 3 decimal places on that. So how do I, what quadrant is the base answer in? I mean, where is that? This is another part of what we're not used to. This is 0 radians. How many radians is this?
It's just plus.
Pi.
It's pi over 2, I know, but what is that? 1.57, blah, blah, blah.
Nope.
This is pi, 3.14, blah, blah, blah. Right? And this is where you add another pi over 2.
So it's 4.671.
Yeah, 4.7, blah, blah, blah. And then this is, 6.28,
Something.
blah, blah, blah. I like it. So where's 0.8632? What quadrant? First quadrant. Exactly. So, and I want my cosine to be positive, so where else could it be?
Second quadrant.
Beautiful. So second one would be negative x. So it's going to be here and there. So it's not a bad idea to give yourself that visual. And so this angle is here, so that's nice. Well, what's the second? Here's the reference angle. That's nice, but what are my 2 primary answers then? One answer is 0.8632.
Two by minus.
No, be better than that.
.628
2 pi
minus.
minus 0.8.
Beautiful. Kick ass. Do it.
Point, okay.
Why do you think I wrote that there? There had to be a reason for that.
Stab you. I mean, what?
I mean, technically, you're not wrong if you put negative .86 there, but you can be better than that.
What? Huh?
Can you make a more specific question?
No.
Okay, I can't answer.
What?
So what is 2 pi minus this? 5.42? Okay. So then how do I write the whole answer?
Plus 2 pi.
Pi.
2 pi.
Yes,
K.
2 pi k, 2 pi k. Cool. Sounds like chupacabra. 2 pi k. All right. Another weird class, that's plenty. So next time, I mean, the next two sections really are all about trig equations. It's just that section 7.5, a little more advanced trig equations. Yay! Okay.
No.
I'm gonna eat lunch and then I'm gonna go get some foodie.
2, 3, 4, 5, and 8.
Oh,
I'm
here.
gonna go eat lunch.
Okay, yeah. Just remind me as we get closer.
Yeah.
So the
I'm gonna go
24th,
score some
so you'll be
goals.
here on Monday. Oh, 24th is Monday. Okay. So probably you could take it when you get back. Give you a little time to catch up on what you did at the beginning of that week. Yeah. Okay. Just remind me when we get closer.
Hey, that's gonna scare me. Should I be on for this?
Wait, what was I gonna ask you? Those are like, so it was such a group identity, and then we have two recs.
Yes.
How do we do that?
You write it and give it to me.
Like the best possible.